Okay, let's do one more one-dimensional example. It's very important that you understand the Atwood's machine, another simple example of Newton's second law. Here's what an Atwood's machine is. We have a pulley with a string over it. The pulley and the string are assumed to be weightless. There is no such thing as a weightless or a massless object, but they're very small compared to other weights or masses in the problem. And on one string we have a 2 kilogram mass hanging, and on the other string we have a 1 kilogram mass. Well, it doesn't want to do it. Okay. I have a 1 kilogram mass moving. There it is. See it? Okay. So, what do we want to find out? We want to find out everything we don't know. We want to find out the acceleration of this guy. We want to find out the acceleration of this guy. And we want to find the tension in the string which connects them. I think we can agree that the tension, the magnitude of the tension, is the same on both strings. It's really all one string. That's why I say that. Okay, so we're now ready to choose a body. And I'll choose the 2 kilogram object to start out. Okay, so here's the 2 kilogram object. What are all the forces on it? There's its own weight, which is 20 newtons down, and there is the tension in the string, which is T, which is in this direction. And you'll note that I am taking G to be approximately equal to 10 meters per second squared. I will almost always do that. Okay, so choose a coordinate system. Well, I'll choose the usual plus y to be up. It's a one-dimensional problem, so I can easily then write the sum of the forces in the y direction is equal to m, which is 2 kilograms, times a, which I'll call a sub 2, the acceleration of the 2 kilogram object, and that's equal to t minus 20. Let's draw a box around that. What have we got? We have one equation with two unknowns, and so we need to choose another body. So I'll choose the 1 kilogram object. What are all the forces on it? There's its own weight, which is 10 newtons down. There is the tension in the string, T, which is up like this. Choose a coordinate system, plus y, like this. Apply Newton's second law. Sum of the forces in the y direction is equal to 1 times the acceleration of the 1 kilogram object, and that's equal to t minus 10. Draw a quick box around that. Okay, so now we have two equations and, three unknowns. All right, so what do? Well, let's choose another body, but there really are no more bodies that are going to be useful. So we're sort of stuck here for a minute, but then we should say, well, now wait a minute. Don't we know the acceleration, the relationship between the acceleration of this guy and the acceleration of this guy? The answer is, well, sure we do. What we know is that the magnitudes of the accelerations are the same. But now we have to stop and think carefully about what the SIGNs of those accelerations are relative to each other. Because if this guy, notice that I've chosen plus y in both of the two cases, okay? So that means if the 2 kilogram object, well, actually, let's use our heads, okay? Let's use our heads. The 2 kilogram object is going to be if it's moving in the positive direction, it's going to be slowing down. Okay, and so a sub 2 is going to be negative. Okay, and if they're moving in in this direction, then this guy will be moving in this direction, and he'll be slowing down too, but he's going down. Okay, so A1 will be positive. Okay, and therefore we could conclude that A1 is equal to minus A2. Okay, think about it a little bit. Okay, so I'm going to simply call A1 A. Okay, so now if I go ahead and solve for A1, okay, so now I can take my two equations and I can rewrite them. Let's rewrite them right here. Okay, so we've got 2A equals, let's see, that's minus 2A equals T minus 20. And then we've got A equals T minus 10. Okay. And now all we have to do is solve those two equations for A and T and ask whether the result makes sense. Okay. So let's see. If I subtract those two equations, then I get that 3A is equal to, okay, better be careful here. 3A is equal to, so that means I'm subtracting the first from the second. And so I get 3A equals 10. Is that right? Okay, so 3A is equal to 10, so A is equal to 3.33 meters per second squared. And then that tells me that T, from either of those two equations, so the tension will be 13.33 newtons. Is that right? Okay. Let's ask ourselves whether that makes sense. That says if I just take these and just let go of it, okay? If I just let go of it, then the acceleration in this guy's coordinate system is going to be positive, okay? And so he's going to accelerate upward, and this guy will accelerate downward, but his acceleration, okay, so this is, I'll remind you, this is A1, and so A2 is minus 3.33. Okay, so this guy is going to have a negative acceleration, but that's right. If you let go of him, he's going to go in his negative direction. Okay, so that's the Atwood's machine. Now, it seemed like there was an awful lot of thinking here going on for an awfully simple sort of problem. And the thinking has to do with the fact as to whether we have made the most clever choice of coordinate system or not. Okay, so I'm going to teach you another Baker's rule. I call this one Baker's rule of the finger. If you choose for one of the objects in the system an acceleration which a coordinate system which points in the direction, in this case, as you see in this picture, plus y is up for the 2 kilogram object, okay, then the 1 kilogram object, you should choose plus y to be down for that guy, okay? And so what you imagine doing is once you've chosen positive acceleration for somebody, okay, then what you do is you imagine your finger pointing in the direction that you've chosen it, okay? And then what you do is when you come to another object in the system, you now follow the string around until you get to the other object with your finger. So you see you've wrapped your finger around the top, and now your finger is pointing down. That should be the positive direction that you choose for that object. Okay, so now when you now when you do the rules of the game, you don't have to worry about A2 and A1, because this guy, if the 2 kilogram object has an acceleration in its positive direction, then the 1 kilogram object will have an acceleration in the same direction. Okay, so let's just quickly run through this problem again. Let me sort of neaten things up a little bit here. Okay, let me sort of erase this. Okay, so let's run through the rules of the game here and see that we get the same answer that we did before. Okay, so now we say when we choose this guy is the body, okay, the sum of the forces in the y direction is equal to, and we're going to choose plus y this way, so it's going to be minus 20 plus t, and that's going to be equal to 2a. Okay, and the sum of the forces in the y direction for the other body is equal to plus 10 minus t, okay, and that's going to be equal to a. And now if you add those two equations, you get minus 20 plus t. I'm going to add these two equations. Okay, so we get plus 10 minus t equals 3a, or a is equal to minus 10 over 3 minus 3.33 meters per second squared. Okay. Why did I get a minus sign this time and I got a plus sign this time? Because the thing that I called a before was this guy's acceleration, and I have flipped the direction of his coordinate system, so it all means the same. Of course, I would get t the same as well. Okay, that's the Atwood's machine, and it's Baker's rule of the finger as well.